now probably is a good time to start. Good morning, everyone, and welcome to the second day of Machine Learning Research School. I hope that you enjoy the lecture yesterday. And given that I see many faces today, that means that you're still with us. That's good. Um, right, so I think today I'm very excited to welcome Amit Sharma. And Amit Sharma is currently a principal researcher, if I remember correctly, at the Microsoft Research India. And he's a renowned expert in causality in machine learning. He received his PhD from Cornell University in 2015. And since then, he's been contributing a lot of fundamental work in causality, especially at the interface between causality and machine learning. And I think that causality actually was not that popular back in the days, right? And people in machine learning didn't really realize the importance of causalities in machine learning, given that these days machine learning has been used a lot in really critical domain like healthcare, I don't know, employment, educations. So it's now becoming very important for machine learning scientists to understand how to teach machine to understand causal relationship from the data. And Amit Sharma, I think, is the best person to give you this tutorial today. So please join me in welcoming Amit.
Thank you so much for the kind introduction, Rikamol. So as he mentioned, yeah, I'm working at Microsoft Research, and I'm very excited to talk to you about causal machine learning today for two reasons. One, I really like this topic. It's very exciting. I've been working on this for 7 years now. I think the second is that we all are thinking about or talking about general purpose AI. There are a lot of ingredients for it which have emerged, like deep learning, generative AI. But what I'll try to convince you today is that the one ingredient missing is still how to reason about cause and effect. Humans can do it very easily. And if you want to build any kind of AI in the future, some of this has to be incorporated. And today, I'm not going to present you the solution because no solution exists. What I'm going to present to you are the fundamental building blocks that will help you assess this challenge. And hopefully, you'll also see solutions coming up in the next few years. But that's still to be seen on how would you scale this causal ML to generative or general AI. So today, I'll talk about two topics split into sessions. The first will be an introduction. And then second, we'll go into how causal machine is used in practice, and also the promise of large language models for causality. The session goal for this session, the first session, is, of course, first to just understand what the heck is causal ML. What's the difference between what you were taught yesterday, predictive ML, and causal ML? And as a side goal, you'll also learn a lot about causality fundamentals. And this is useful even outside machine learning. The second thing which I'll talk about, and this is often very confusing, is when is causal ML useful? So people often sort of confuse this because you might think that causal ML is always useful. It sounds causal, so it must be good, right? It's not true. There are cases where you can do easily as good with predictive ML. So I think this skill is very important to know where you should actually apply it. And then finally, we'll talk about what you can achieve. So you can make better decisions. You can do root cause attribution. And sometimes you can also predict well if you have a causal model. All right, so with that, these will be the three sections. What is causal ML? The fundamental concepts. And I'll talk about three main applications. If you have any questions during this, feel free to just raise your hand. I believe there are mics, and then you can just speak up. I have lots of slides, warning, so I don't want to go through all of them, right? I don't want you to suffer through all. So please ask questions, interrupt me. Your goal is to make me not finish all the slides. OK, so what is causal ML? Some of you, obviously, all of us are knowing about cause and effect, right? So you must be thinking it has to be something about inferring what is cause, what is effect. But that's not how machine learning evolved. In fact, all the successes of machine learning today, all the kind of hype that you see, has come from predictions, which just says, what does the data say? Can I extract the maximum information from a given data set that I have? And so this has powered recommendation systems. This has powered even dating websites, finance, fraud detection, medicine, disease detection, X-ray analysis, and so on. But increasingly, people are finding out that there is another class of problems, which are decision-making problems. So these are about what action should I take. Right? So you might think, like if you're in a company, you might be thinking about marketing, or which customers should I reach out to? Which customers should I give discounts to improve my sales? Doctors might think of what treatment will have the best impact on this patient. Again, you might think of, if you're in the government, what kind of messaging should I do? Should I reach out to public through email? Should I reach out to public through phone calls in case I have an important message to communicate? And in the case of climate, you can also think about, would this government regulation increase or decrease air pollution or decrease temperature, right? So these are kind of hard policy questions. Some of them come from economics, some of them come from public policy, some of them just come from the desire to make more money. But there are important questions which are outside prediction. And sometimes, these problems overlap. And this is one of the reasons causal ML is not really something you'd see in many applications. So take this doctor, for example, right? In their case, they wanted to know, given an image, does the X-ray detect a disease or not, right? And maybe it's a tumor they're detecting. The interesting part is that in this case, accurate prediction may also mean accurate decision making. And what I mean by that is once they have discovered that this person has a tumor, the decision might be the standard thing they do for treating tumors, right? So here the decision was not really the hard part. The hard part was knowing what kind of disease this person has. That's a classification task. That's a prediction task. But then the decision is pretty simple. You just then do what you do for tumors. Right? And so that's why you might see many applications where people say we're using machine learning for decisions. But really, it's the kind of cases where the decision is an obvious one. And sometimes they don't. And this is what is today's topic. You might have a prediction task, which is predict the customers likely to churn, right? A very common task. And in marketing, people would say, this is very important. I want to know who might not renew their contract, and so that I can go and tell them something, right? So think of Netflix, think of Amazon Prime, any of these kind of subscription services. But here what's interesting is that the decision task is different. So now you want to know who should I provide discounts to, right? Your instinctive reaction might be, hey, the people who are leaving, let me just flood them with discounts, right? Give them enough money so that they stay. But just think about it. Why would people be leaving, right? One reason might be they just don't like your service, right? They're not using it. So even if you give them discounts, it's unlikely that they might all come back, right? And in fact, they might all, in fact, go away if you give them discounts or not, right? Similarly, the people who are very active in your service, it's not worth giving discounts to them as well because they might as well stay, right? So you might think these are my best customers, I should give them discounts so that they stay. But for all you know, they might have stayed anyways, right? They just love your service. So maybe one hypothesis could be you need to find the people who are on the edge, right? They kind of like your service, but just if they had a discount, they might actually stay with you, right? And this is just a hypothesis, right? I mean, different customers, different businesses will have different patterns. But this is just to show that in these kinds of cases, we can't really just take a prediction model and run with it. And the primary reason is that there is a clear difference here between what is correlation and what is causation, right? So correlation here, for example, is just that people who don't use your service are going to churn out, right? That is going to happen. But it's probably another angle that you want to look at is what is the effect of discounts on them, which may be different for different people. So one way a lot of people look at it is through a graph, just sort of non-formally. This is just saying that the product usage would affect both whether a person renews their contract or whether they get a discount or not, because the discount is you giving the discount, right, based on your model. But the interesting part is that there might be no relationship between discount and renewing your contract, right? So if you're in a world like this, the right decision is not to give discounts. Doesn't matter. People are going to renew or not renew based on product usage, right? But maybe you're in a different world. Maybe the discount matters. Maybe there is an edge between this renew contract and discount, and that's what you need to find out. But I think the key message here, if you just want to look at this one slide, is that the prediction model will tell you nothing about the existence or non-existence of that edge, right? And that's what we want to find out, and that's what Causal ML is. Causal ML is hoping to be able to give you decision actions which are based on understanding this effect. And often, sometimes, like if you're outside computer science, people might say, hey, why are you trying to justify this so much? Like Causal ML is just fundamental, right? And that comes from public policy, economics, like many of the education, health even sometimes, where people say, look, I'm not interested in prediction, right? I'm just interested in estimating the effect of an action that I want to do, and I want to be justified before doing that action that this might be a good action, right? Or sometimes, hey, I have done this action, or the government has implemented this policy. Can you tell me how much effect it had on the population? So in those kinds of questions, they're kind of causal questions from the get-go, right? So you might have, what's the best way to share an important public message? So here you want to find out the impact of this public message on people's behavior, right? Similarly, if it's about government regulation and air pollution, you're not really interested in predicting air pollution. Maybe you can do that. That's a different task. But here, you're interested in whether this government regulation would increase or decrease it. Very different questions. And again, what might happen is that you may get, again, fooled by correlations, right? So now in a different way, more subtle way. So it's not like whether discounts cause or not cause, right? In this case, you have of course, you have a practically good idea that giving someone a message will impact their response rate, right? Similarly, here also, the government might have an idea that if they make a policy, it is going to change air pollution, right? But now the kind of things that happen are very kind of tricky biases. So in this case, you might have a selection bias, which means in your data, you might see that whenever you text message someone, the response rate is the highest, right? Now, as good data scientists, you would say the data should speak, right? I should only trust the data. So therefore, I will conclude that sending text messages is the best idea. But for all you know, that data might have been collected by someone on school students, maybe, or college students, right? All young students. It's unclear how that would pan out when you generalize it to old people or the general population, right? Maybe they would like phone calls. Similarly, in the government regulation case, maybe you have some data about other states, right? And the other states' pollution decreased. That's great. So the pollution decreased in other states. The other states look kind of similar, so maybe it should decrease here as well. But even here, there are very sort of subtle kinds of biases that may come in. Maybe the other states have a different kind of industry, right? Maybe they're on coal, you're on wind. Who knows, right? Maybe they have a different kind of production. So these kinds of things are very hard to do unless you have a proper framework for reasoning about them. You might say, of course, if I know about this industry change, I'll just include that as a variable. But it just gets very hard if you keep thinking about it, right? And so the topic for today is how to solve these problems in a principled way, right? I'm sure if you have worked with data, you might often have seen such problems, and you might have quickly devised some kind of quick solution, some kind of quick hack. But the goal for today is not to do those things based on application, but to think of if you had to build a general purpose AI, how would you do this in a systematic way so that for any kind of question, it can give you the correct answer. And essentially, that would mean we want to learn causality, right? Whatever is in our heads of how we learn causality, we want to impart it to a machine. And so now you must be thinking, like, this guy keeps saying causal, 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 but he hasn't really defined it, right? And I won't define it, this disclaimer. One of the reasons is it's really hard to define. It's a philosophical question. So maybe I'll define it in math, right? Things that you would understand easily. So causal ML, you can just think of, is about inferring the best action and often the effects of actions in general, right? So you might just be interested in the effect. So think about it, like whenever you have some data set and assume it's some true function is y equals fx of u plus some epsilon error, where u is unobserved. In prediction, all you care about is I just want to fit this hx really well so I can predict y hat. Right? In causal ML, often that's not of interest. What's of interest is this kind of partial derivative between f of x and x, meaning how would y change if x changes. Right? And as you can see, I think the tricky part again immediately becomes that this u might be unobserved, and so you have to somehow control for that. You can't just let u sort of vary as it does because it's a partial derivative. So that's the whole challenge. So with this background, I'll talk about 3 decision-making applications today, actually 3 applications of causality. The first one would be decision-making. I mean, we all want to make good decisions. Computers also would like to help us to make good decisions, right? So we'll take this one example where suppose you are the mayor of a city and you want to make people healthy, lower their cholesterol, right? And we'll see what happens when you have some data where some people don't cycle, some people cycle, and you want to know, should I just give a lot of benefits? Should I just give free bikes to everyone, right? Would that help their cholesterol? And so that's the decision-making scenario we'll study. The second thing we'll study is going backwards in time. Right? So in the city mayor scenario, you wanted to go forward. You wanted to see what is the best decision I can take to improve my population's outcomes. In the second one, assume the decision has been taken. Right? The world has moved on. Now you just want to learn from it. Right? So you want to do root cause attribution. Why did that happen? So in this case, we'll talk about a machine learning model. A machine learning model makes some predictions. They seem weird. And you want to understand why is the machine learning model making those predictions, and how can I improve it? Right? But also, you could do it for any system. But also, you could do it for any real-world system. Right? So you could ask, I have some kind of a water plant. It sort of processes water. Suddenly, the quality has gone down. Which of my components has failed? Right? So you might think of drawing some kind of state diagram and figuring out what sort of failed. Right? And the last application we'll talk about, this is kind of the darling of machine learning, like out-of-distribution generalization. Like in Europe's ICML, you'll see so many papers these days. And so we'll just take a small part of it and just see how causality could be helpful. Right? This is, again, emerging research, so the future is unclear what will actually happen. But it'll be interesting for you to understand that even in prediction sometimes, if you're really caring about the quality of your outcomes, you might want to consider causality. So for example, here, you might have satellite data. Some is from America, some is from Africa. And you just wanted to detect the building type, right? How many buildings there is. That's actually a very nice thing to do because you can estimate economic output based on that. But the problem might be that the data you have is from 2000s. The thing you want to predict is from 2017. You might have data from America. You want to predict about Africa. So all kinds of hard things come up when you want to generalize to new distributions. So with that, I want to summarize the motivation by just saying, think of causal ML as just causality being introduced into machine learning. And I hope through these examples, you can understand how it has to be a necessary ingredient as we build more and more capable AI systems. Any questions so far? Yes, yeah.
This might be a little bit This could be a digression from the topic. I came from a physical science background, and causation is a holy grail.
Yeah.
So could you give a comment about causal machine learning that would maybe enable science? Let me give you an example. When Einstein proposed general relativity, he's looking for causation why gravity has an effect. So is there an application like this for causal machine learning in science?
Yes, I mean, in some sense, science is built on causality, right? So the way I would say it is that those kinds of applications were easier to find in the early sort of decades of science, or I think 1800s, 1900s. Because if you even remember Robert Hooke's spring experiment, where he was trying to sort of stretch the spring, I'll talk about what they were essentially doing were interventions and counterfactuals, which are really the fundamentals of causal ML as well. So maybe once we get there, I'll give the physics example. But to answer your question, I think today, when I hear scientists, especially biologists or physicists who are working on their experiments themselves are a system. Like it's a large system with many sensors and many kind of components. So one thing I've seen people use causality there is kind of just understanding their system end to end, right? So things like, if I change my sensor here, how will it change my observations and will it make it more robust? And vice versa. My system suddenly is giving me some weird results. Can I quickly debug this system? I'm not an expert on the fundamentals of science, so I don't know how they're using causality today there. But definitely, I think in just these large-scale experiments, like think of the Large Hadron Collider, like a lot of the things that go in kind of debugging and understanding the system can benefit from causal ML.
Hi.
Any other questions? Yeah.
Is there a difference between explainability and causality? Explainable AI is one of the newer areas of natural language processing that I've seen do some things that are very similar to causality. So if I can think about causality versus explainability, is there a sort of difference?
Yeah, so the way to think is that explainability is your goal, and causality may be one way to reach it. There might be other ways to explain a model as well. So we'll talk about one example of using counterfactual reasoning to explain a machine learning model.
So you talked earlier about the difference between decision making and prediction problem, but I wonder about the fundamental, maybe more technical differences between them, because as I can iterate all decision options that I have and then make it a prediction problem. So to me, they seems like prediction is a more generic term, and decision making requires prediction still. I don't see the technical differences between the two.
Yeah, that's a good point. Yeah, so I think I kind of abused the term prediction here. Let's just come back. Yeah, so prediction is a much more general term. In fact, you can also think of causal ML as predicting the effect of actions, right? So that way you're right. Yeah, I think causal ML also ultimately will predict things. It's just that you predict different things. So when I talk about predictive ML, usually people talk about predicting the outcome, like whatever the final outcome that you're interested in. Whereas in causal ML, you're interested in predicting the effect of actions.
I see. Thank you.
OK, let's dive in. So as I mentioned, what I'll do is first a little bit of context setting. So this might seem boring to you, but I think it's important to understand three concepts before we move on to some real-world applications. So we'll have to understand what's an intervention, counterfactual, and what's a causal graph. And I promise you, once we learn these three, there will be interesting things you can do with them. So let's come to this intervention. And because there was a question about physics, I'm actually going to take a physics example here as well to define it. An intervention is just a formal way of defining taking an action, right? So I would say an intervention is an active action taken that changes the distribution of some variable t. And what I just want to highlight is that it's different from just observing two different values of t. So in the cycling example, an intervention would be, in the observed data, this red young person has no cycle. Intervention, you give him a free cycle, and now you see him cycling on the streets. Right? What is not an intervention, and mathematically, you can represent this as the do operator. So this comes from Yudia Pearl's work. The notation is quite important here because if you're just looking at the data, you might just say it's probability of health given cycling, age, and color. And here, color is just the color of these stick figures, right? Don't read too much into it. And then interventional data would be some P star, where you gave someone free bikes. And then the health would be dependent again on cycling, age, and color. But this is a new distribution, right? This is a distribution of free bikes going around everywhere. And so just to differentiate these two and also tell you what's common between them, we try to use this do operator. which is just saying that the cycling was introduced by someone else, and it's an intervention in the sense that the same person who was not having a cycle before has been given a cycle. What is not an intervention is when you don't keep other variables constant. So let's say if in this case, this red person did not have a cycle, and I don't know what the mayor did, but he first gave him blue clothes and then also gave him a cycle, right? And so now this is not an intervention, right? Because even if you see that this person now is more healthy, you don't know. I mean, it could be because of cycle, it could be because of his blue color, it could be due to many other things, right? So that's one thing to note, that intervention is a very simple concept, but the hard part is, how do you do it keeping everything else constant? If you remember classical physics, there's this experiment by Robert Hooke, who was trying to just find out how much the spring sort of moves if you exert some force on it, right? So think of two ways Robert Hooke could have done that experiment. The first is he fixes the spring to the wall, stretches it, and he can measure the tension, he can measure the movement. The other is he can have the spring in his hand and then push it like this once, pull it like this once, sometimes move his hands, right? Obviously, he didn't do the second thing because that would not be an intervention. Because what you're doing there is you're moving the spring, but you're also moving your hand. And so it's very hard to know what's the effect of just the spring, right? So that's maybe one way of thinking about physics and causality. People were doing it, but I think they never called it causality. It was just so obvious to them that they would just do interventions correctly, but not have the formal framework for it. The second important concept, again, one of those things which is very easy for humans to understand, but so hard to put in math, is counterfactual. Okay? So I actually didn't know about this word. I think I started speaking this word when I was 25. So before that, I didn't even know what this English word was. But I could intuitively do it, right? And it's just basically just what would have happened if, right? We all do what-if analysis. And so here, let's take our cycle guy again. The intervention happened in the real world, the blue world. He now has a cycle, right? But often what we want to know is, hey, what if I did not give him the cycle? Would he still have become more healthier? Maybe he was already on a good path, right? And so that's what the counterfactual essentially means intuitively, is that you've done something in the real world. Now you want to go back and ask what would have happened if just that thing did not happen, but everything else remained the same. And if you look at this expression, you'll know what I mean. It's really hard to understand counterfactual in probabilistic language. So that's why Yudia Pearl had again to invent some new notation to describe a counterfactual. So here he says that, okay, your health at t+1 in the real world was health star. Your health as t was also health star. You were cycling at t+1 in the real world. I saw you, right? But now I want to ask, what would have happened if I did not give you that cycle at t+1, right? And so that's how you write this weird expression. Later on, we'll also look at how you can estimate this expression. But for now, I think it's just two things are worth noting. One is that this is a really hard quantity to calculate, as you can imagine. This is sort of saying not just what is the health at t+1, it's also saying, tell me the health at t+1, given that without this intervention, the health would have been this. I already know that. I've seen that, right? So it's a very sort of hard problem to do. But also at the same time, if you look at the English description of it, maybe it's something we can maybe succeed in some cases, right? It doesn't seem so hard. So all we are saying is, given that the person started cycling and improved their health, what would have happened if they did not start cycling? But everything else remained the same. And now we have the necessary tools to define the causal effect. You can say that x causes y if changing x leads to a change in y, keeping everything else constant. Right? And if you're with me in this talk, I think this phrase will keep coming up again and again. In statistics, you might call it conditioning or controlling. But I think really the intuition of that is how do you keep the other variables constant while you're measuring all these effects. Right? And then the causal effect can simply be the magnitude by which y changes. You're given a unit change in y. So you can write it as probability of y given do x equal to 1 minus y given do x equal to 0. So 1 and 0 are just standard values. You can use any value here to compute the causal effect. And both of these are actions, right? Remember, so it's not like you're just comparing the observed data to what you did. You have to compute what would have happened if you gave them X versus not give them X. What's the problem? Well, one of the things is never observed. We live in only one world. What do? You might do X equal to 1, then you have not seen X equal to 0. You might do nothing, X equal to 0, but then you have not seen X equal to 1. Right? So one solution could be that, hey, I just don't like this. I won't look at this. This is too complicated. Let me just look at my data. Let me see how X and Y vary, and let me just fit a model. Right? So that's what I was calling predictive ML earlier, but that's a kind of a very standard approach to solving these kinds of problems. You'll just fit a very expressive function that connects X to Y, right? With the assumption that if your function is really expressive, it can capture all kinds of relationships, right? So what you might just assume is, hey, I didn't observe do X equal to 0, but not for this person, but maybe some other people or some other location had X equal to 0. Let me just take Y from that. And you'll just try to fit a model predicting X, Y from X, right? Now, as you all discussed in the previous section, this can backfire if X and Y share some correlations, right? And I'll give examples later as well. But the simplest example here could be that the people who are cycling maybe are younger, right? The mayor just did I don't know why, he thought he just needs young voters, right? So he gave all the free bikes to young people. If you do that, then you'll have a problem. And now our goal is more defined, right? Previously, our goal was causal ML. Then we made it about decision making. Now it's even clearer. We just want better approximations of this do formula. Final concept is the causal graph. The most loved, most hated concept, depending on which side of causal ML debate today you are in. I happen to love it, so I'll present it. So causal graph encodes assumptions that help you estimate this unseen. It's one of the ways to estimate the unseen, right? Now, if you already know there's nothing in the data, what can you do? Well, you'll think about some assumptions you can make, right? You have to make assumptions, right? There's no free lunch here. You haven't seen that data. You're not willing to use some other area's data, right, and so on. So what we do is we make some principled assumptions about what we believe might be happening in the world. And this has to come from domain knowledge. I mean, we'll talk about how you can learn this partially, but more often than not, for real-world problems, you need to know how your variables are affecting each other. So for example, here you might say, I have the age, I have some other attributes of people, and so age should affect cycling, maybe, and then also it should affect health for sure. And then the other attributes may also affect cycling and health. And we also saw another example from product usage earlier, where you were trying to build a graph of usage and churn. And so really what a causal graph is helping you do is express the key assumptions about what you believe matters and what you believe would affect the outcome. Here's a failure case, just to whet your appetite, right? The reason I said it's also the most hated concept is because people would ask, why, who would give you this graph, right? It's very hard. I mean, I just made a toy graph, but in general, if you think of a real city, even Bangkok, right? These might not be the real variables. Maybe there are 10 more variables I should consider on what makes people cycle. Maybe it's about do you have cycling lanes or not, right? Maybe it's about do you have helmets or not, I don't know. So it's really hard, right? But at the same time, it seems like there's no other option, because how would you avoid problems like these, right? So I give you this data. These are two variables. Call them x1, call them x2. And I see that it's going up and up as the years go by. From 2000 to 2009, there seems to be a perfect match between these two variables, right? Now, if I'd asked you predict the black line based on the red line, you'll say that's an easy task. I will build a time series model, and I'll be able to predict with high accuracy, right? But now what if I told you what these variables were? Just have a look. Just read what these variables are. This is real data. So this is from the US. The red line is the total revenue generated by arcades. And the blue line is, sorry, the black line is the computer science doctorates awarded in the US. All of you might immediately see that there is no causal relationship. Any model built using the red line to predict the black line will fail at some point, right? Or you might even laugh at the person who made such a model. But the fact is, we could have done the same thing if we did not have this knowledge. And that's one way of thinking about why you need more assumptions in addition to the data. Yeah.
Quick question on the causal graph. Is it better or worse if the causal graph is most elaborate as possible? And do we need, another is, do we need to put in any unknown assumption, unknown variable or unknown assumption in there? Yeah.
Yes, so I think it's better to have as many nodes and variables and edges as you can. And it's even better to say when you don't know, right? So if you have unobserved variables, it is good to express them as nodes in the graph. There are algorithms available which can deal with unobserved variables. The only thing you have to keep in mind is never put in an edge if you're unsure of the direction, right? So like, if you don't know what are confounders, you can add a few more confounders. That would not like maybe create such much of a problem. But let's say you're unsure about A causes B or B causes A. In that case, you should maybe just have a straight line between them. Like the worst way you will suffer is when you reverse the edges of even one edge in your graph. It can completely throw you off. Yeah. Any more questions? OK, so let's do some math here, right? A causal graph is not just a wishy-washy object that you draw in Excel or Paint. It actually has a mathematical interpretation. So one, of course, it helps you, right? So even if you're not a math expert, even if you're, let's say, again, just a decision maker, like the mayor, right? A causal graph helps him to understand what assumptions you made to provide him this analysis, right? So that's one benefit. But for you, the benefit is also that it's really a mathematical object. So edges are denoting direct causes. So here it means A causes B. But also the graph implies conditional independences that you can just read of this graph, right? So we'll talk about how to derive them. So one thing you can see is that I say A is independent of C. So let's look at A, let's look at C. This seems easy enough, right? I mean, they're just happening on their own, and then they affect B. But then you might have things like D independent of A given B. This requires some thought. But again, you can look at this graph and understand that D and A are only connected by B. So A causes B, B causes D. So they're sort of events going on in sequence. But it makes sense. Like if you just fixed B, or if you kept B constant, there's no way A and D could now affect each other. So this is actually the intuition, but these are formal rules. The easiest way to think of them is that there are kind of three kinds of nodes that can exist at any point of time in your graph. If there's a node like this, which is like a chain or a straight line, if you condition on X, so read X as A here, right? So X and A are the same, then you would block the path, meaning you'll separate the causal connection. If you condition on A when A is just sort of going in both directions, like a fork, even then if you condition on it, you're going to break the information flow, and that's also a separation, right? The only thing is the last one, which is like when A is so-called collider, so two things are simultaneously causing A. In general, that does not matter, right? We just saw it here. If both A and C cause B, who cares? Like A and C are still independent, right? They're just coming from different processes and causing the same thing. But what's tricky is that the moment you condition on A here, it would create a relationship between its parents, right? So just to understand D-separation, you just read off a graph and look for these three kinds of nodes. As long as you can find that the causal path is blocked, then you can say that the path is D-separated. So let's do an exercise, right? And again, I think if you don't understand this really well, it's not needed. This is something today algorithms can do. So if you give a graph to an algorithm, to an open source library, you can easily find all these kinds of D-separations, right? But I think just getting the intuition is important. Really what we are looking in the graph is to tell us what independences I can assume for building my model later, right? So let's do an exercise. So suppose this is your graph, T, Y, and H. And suppose I just want to understand how to block this edge from t to h to y. Anyone answer what would you do to block that causal path? I'm just looking for what kind of node age is between these three, and then should you condition it or should you not condition it?
Condition it on age.
Yeah, that's correct, yeah. Thank you. So yeah, you condition out age, right? And it's also very intuitive. Again, let's take our mayor example. The mayor should have sort of thought about the age, right, when he's trying to give away different cycles, right? So if he really wants to understand the effect, pure effect of giving cycles to y, which is health, he should be conditioning on age and only comparing people of the same age with or without cycle. And the last thing, this is kind of subtle. It took me some time. I mean, I was working in causality for some time. I didn't know this. So that's why I'm telling you right now, so that you know this. The assumptions are not the edges you put in. The assumptions are actually the edges that you omit, right? So here, the assumption is not that age is causing t and y. Well, OK, it is kind of an assumption. I didn't assume the other way around. But having this graph, at the end, you can still say that the effect of the age to t arrow is 0. That's allowed. That's one of the outcomes you'll find, that age and t are just not related, right? But the real assumptions here are more about the variables you did not include, the edges you did not add, and so on. So that's very important, right? Your assumptions are really the missing edges and also the direction of edges that you made. And the relationships have to represent something stable and independent, right? And that's why we call them causal. So the only relationships to put in which are stable across domains, stable across location, time, and so on. And finally, it's not always possible to learn this graph fully from the data. I will tell you the algorithms in the second part of this lecture, how to learn a graph. But it's just know that there are limits to those algorithms. And so any part of causal ML you need to do is you would need some kind of graph, some kind of assumptions that you put in outside the data. And if you're wondering like why everyone doesn't use causal ML, this is your answer, right? Imagine you're building a large-scale model like ChatGPT. How would you get this graph? Right? It's a hard thing to do in general. One of the ironies is that ChatGPT can discover this graph based on text. So leave that irony in your mind for some time. I think we'll talk about that as well. But this is kind of the tricky part about causal graphs. You need to know how to get them. So one option could be you just use your domain knowledge, right? So you might say, I want to estimate the effect of my customer rewards program. I am in this company. I know how my system works. I know how my customers react. So I'm just going to build a graph based on common sense, like the pre-spends of a customer should affect whether they are signed up for this program, and when they sign up for this program should affect what they'll spend later, right? Similarly, I might think the sign-up month matters a lot. My people sort of decide when to buy, when to not buy, based on what month, what weather it is, and so on. And then finally, you might also say there are some other variables I have no idea. Let's just call them Z. They might also be affecting how they sign up, right? That's one example. So you could sort of just design your graph based on the basic assumptions that you might have. Some of the other successful examples are where you just use your domain knowledge based on a real thing, right? So I gave this example of a physics simulator. If you're building a large physical experiment, you have built it, so you know the structure, right? There's no need for an assumption. Just look at how you built it, look at the diagram of that system, and that's your causal graph. In computer science, I'm giving you an example of a microservice. So microservice architecture typically involves a lot of API calls matched together. The pattern in which the API calls are happening is exactly your causal graph, because that determines how information flows between different variables. Cool. So now we are done with our three concepts. Any questions on any of them, the causal graph? Has anyone ever built a causal graph in their life?
Sorry, I have a question. So you said earlier, I believe that you can use unknown nodes for the graph. I have a question, not sure answered yet, but how do you account for, so in real life, there's going to be like other variables, like extraneous variables, while in like the simulated or the algorithm model, you can make things very constant there. So how do you account for like unknown variables? For example, there could be a discount going on, but at the same time, there could be like a friend telling the user like, hey, you should like keep using it. So how do you account for those other influences?
So I think the best answer is you try to do the best you can. So here, for example, and I'll tell you why. It's not just a cop-out. I mean, there's a reason, a statistical reason why you do the best, right? So here, as you said, there might be some friend effects, right? So maybe you have some Facebook data or whatever, right? If you have that data, you can add that also as a variable and measure what this person's friends are doing. You might also add other data. I mean, someone could go to the extent of saying, I want to include the economy of the country, right? If the economy is increasing, people will spend more. I want to include the inflation rate by the central government. Sure. So what you can do is, depending on what kind of product you're selling, you can use your best judgment to add as many variables as you can. What seems to happen after some time is essentially the phenomenon of diminishing returns, right? The first time you start, your answer might not be so good because you miss the social effect, you miss the financial effect, right? But as you build this analysis and as you keep adding more variables, after a point, any new confounder or any new variable may not be able to add so much information compared to what you already have, right? Because these things are also correlated in a sense. So it's really sort of trying to get the largest net possible of the confounders you have. But beyond that, yeah, I think it's unknown. So, yeah.
Yes. Quick questions on some possible restriction on the graph. You mentioned the deseparation. That's remind me of the Kohler's works on the graphical models, and they tend to encode it in terms of a directed acyclic graph, right? Correct. Do we need to have those restrictions in encoded domain knowledge into the causal graph?
Oh, yes. Oh, yeah, that's a good question. I forgot to mention. Yeah, so you have to create the graph in a way there are no cycles. Yes. There are some advanced methods which can deal with cycles, but I think for the most part, it's better to create graphs without cycles. It simplifies the analysis. Yeah.
Hi. Suppose if we do actually draw a very good causal graph, and we actually have a lot of variables that we are able to include in this equation.
Yeah.
How do we actually evaluate whether the estimated effect is something that is close to the truth?
Very good question. Hold it for some time. I will come to it in the second part of this session, after the break. It's the most important question, so I'm glad you brought it up. But I think let's just wait a little bit. Let's see some applications of estimated effect, and then we'll come back to how can you validate it. Yeah.
So from your deseparation slides, I understand how to find if the two paths are blocked, but I still don't understand what it means for two nodes to be deseparated. Could you explain it in a simple terms?
Sure, yeah. So it just means that no causal information can flow between them. So meaning that if you change one of those variables, the probability that the other variable would be affected is 0. So you can assume for most part that under that configuration, they are independent. You can change one without changing the other.
I see, thank you.
Yeah, so I think one way, and I don't know if people are familiar with information theory, you can also think of the graph as just sort of a flow of information, right? And so usually information just flows, so C goes to B, B goes to D. So if C knows some secret, it can tell to B, B can tell that secret to D, right? Deseparation is just saying that you introduce a block in that path, so now that secret cannot flow. And D, for example, if you condition on B, D would never be able to know the secret that C knew. Okay, so as promised, I think now we'll not talk about abstract things. We'll talk about real problems, right? So we'll talk about how these three concepts, intervention, counterfactual, and causal graph, can help us make better decisions, can help us assign root cause better, and also help in out-of-distribution generalization. So as I think someone had pointed out earlier on this question of thinking of estimating the action of effects also as a prediction, here's what people do in this problem as well. So you say I have a decision-making problem. Given a target outcome, I want to know which action would maximize that outcome. Right? Rather than sort of modeling this whole problem at once, one way you can simplify it is by say that I'm going to take the list of my actions and separately compute this quantity. I want to compute the causal effect of y, which is the outcome, with action A1. So y given do A1. I'll get some answer. Then separately, I'll do probability of y given A2. I'll get some answer, and so on. And so you can essentially convert this decision-making problem into just a ranking problem over the different causal effects. Right? And that's typically what's done as well. And ultimately, what you want is to choose the action that will give you the maximum benefit, right? The maximum causal effect. So that's reduction one. You reduce a decision-making problem into a causal effect estimation problem. Now we'll talk about reduction two, which is how do you reduce something with a do operator to something you can estimate with data, which means you have to somehow remove this do operator. The best way people know today is to do randomized experiments. So if you have the power to do it, then in causality, the best way is for whatever action you are trying to evaluate, try to do a small randomized experiment. Right? So an example would be you roll the die. Some people get a cycle, some people don't get a cycle. Right? Of course, as a mayor, you should not do that. You'll be voted out. The people who did not get it would ask you why. And if you say you roll the die, then you're out. But in some cases, you can, right? Like if you're running a large e-commerce website, as I described earlier, people do experiments all the time, right? Some features are shown to some people, some features are not shown to some people. And so that's the best way to do it, right? And why does it work? Because by randomizing the decision of who gets a cycle or not, who gets the action or not, you've essentially made this problem into a simple problem where do of A is the same as just the distribution of A observed. Right? Because remember, we were talking about keeping everything else constant. Here, just by randomizing, in expectation, you have made sure that in the data, if you see someone without a cycle and someone with a cycle, there is no other difference because you literally randomize them. Right? So this is for free. You're keeping everything else constant, counts for free, so you can do that. Right? But in most cases, we cannot intervene. And so what we are really provided with is really messy observational data. So you'll get not random, you'll get people who have not cycled, and maybe they have high cholesterol. And you have people who have cycled, and they have low cholesterol. Right? But when you look at their distribution, they're very different. Some are old, some are young, some are whatever, living here, some are living there. It's really hard to know whether we can adjust this difference just based on their cycling. That's in all applications. This is the kind of data you get. So what I'll do is I'll go through a series of methods on how you can estimate this difference and how you can estimate the causal effect. We'll go from the simplest method, perhaps discovered early 1900s, and then slowly we'll move on to methods using deep learning that have come like 5 years ago or something like that. Right? But I think if you get the simple method, it's much easier to then understand the complex methods as well. So the simplest method is you want to match data points, right? So you want to make sure that if someone has an intervention and not, someone has a cycle or not, they share the exact same confounders. And again, I think to the question that was asked, so honestly, I don't know how many confounders there are, right? But the best you can do is whatever confounders you have observed, like age, color, height, and so on, whatever you have about the people, you should make sure that at least that remains the same. And the assumption is, to the extent you have covered a wide diversity of such variables, this would tend to the true confounders. So what I can do is I can say, okay, I will just identify pairs of treated or people who were given the cycle and untreated individuals and make sure that they are exactly the same, right? So I can pair a kid with a kid, I can pair an adult with an adult and an old person with an old person. And this kind of makes a lot of sense because now when you compare just these pairs of people, the only difference is the cycling. Right? Of course, in practice, you won't find such digital twins. There are only a few twins in the world. So what will happen is you'll have to do some approximation. So you'll do some distance, right? So you'll have some distance metric between any two people. And you'll say that I'm going to compare the observed health of two people only if their distance is less than some epsilon, right? And once you have that, you can estimate the causal effect just as an average over all these matched individuals. A problem, of course, comes is the same, in all statistics, which is bias and variance. If you do that, you have to decide what should epsilon be. Right? If you choose a very low epsilon, you'll have lots of people in the bottom. Poor people never got selected anywhere. Right? So what that means is whatever estimate you calculate, it would not be true for these people. Right? And if this population is a large one, then you're not really calculating the average effect in your city. You're just calculating the average effect for some people. Right? If you make it too large, this set will become small. Now you can make a statement about almost everybody because you will find a match with large epsilon. But now the probability that it's actually a causal effect goes low, right? Because now you're not really conditioning properly. You're just kind of admitting anyone anywhere in your analysis. And so that's kind of the holy grail here. Like reduction 1 was a simple ranking reduction. I think in reduction 2, when you want to go from do operator to a statistical estimator, you always have to go through this challenge. First, if you have a very stringent matching criteria, you'll have very few matches, you'll have high variance. If you relax the criteria, you'll have bias. You won't have the true causal effect, right? But again, there's no real answer. It just depends on how much data you have, how much kind of error you're willing to tolerate, and so on. And finally, there's also a more practical concern, is that sometimes you might just not have enough people of one condition. So maybe you might not have enough people who were given the action, or opposite, you might not have enough people who were not given the action, right? So this becomes less common, I think, in these kinds of scenarios. Maybe, you'll find some 60-40, 30-70 kind of relationship between treated and untreated. But especially think of like the power law scenarios, like think of language, right? Suppose you're trying to model language, and you're trying to think of treatment as this word is in the sentence, and untreated is the word is not in the sentence, right? So now the probability of getting treated might be high given the rest of the sentence. So for example, I'm saying this is a great session. So if I want to just predict great, the probability of great coming in the this is a dash session is high, right? But then there are so many words in the English language. How will you think about the probabilities of all of them? Those are all actions you can take, right, if you're a generator. Or similarly, in sort of customer applications, like you might have such a long tail of customers. And so this problem often comes up in practice, and you need better ways to deal with these, right? You can't just say, I'm going to estimate probabilities, because that's going to fail in these high dimensions. But still, the intuition is good, right? Let's keep with the intuition. Let's develop a method assuming things are nice and normally distributed and all of that. But we'll come back to now the problems just after a second. So this intuition leads to a popular principle, which is known as the backdoor criterion. This was again developed by Yudia Pearl and his colleagues. And it says a very simple thing, that if you ever want to remove this do operator from your expression, one way to do it is to condition on these common causes of y and t, which would be, let's say, z here. And then you average out over all of them, right? So imagine if z was just an identifier for whether you're paired or not in our cycling example, then all we are saying is, we'll first pair people according to Z, we'll compute their difference of health, and then we'll just average over the distribution of Z, which means we average over all pairs, right? The only thing you need to make sure that Z is a valid adjustment set. And I mean, again, this is not something you need to compute now, because again, there are tools available that will do it for you. But often the common ones are the set of all parents of T. So the set of all parents of your action is a backdoor set. The common parents of T and Y is also a backdoor set. And then there are other more complicated ways of defining this set as well, right? But the intuition is that the union of all features may or may not be a good backdoor set, right? So it's not as easy as just taking a large data set and saying that I just want to add everything else, for the simple reason that some of those might actually be children or might actually be caused by the treatment, right? Or they might be caused by the outcome. The moment you include them, it will bias your estimate, and it would not be the correct thing to do. And why not always use parents? Because sometimes parents features are unobserved, right? That's why it's not such an easy problem. You can't just say, oh, I'll just use the parents of T. Why bother about all these criteria? The thing is, like, parents might not be observed, so then you have to think of what other variables would effectively do the same thing. Right? And if you want to get the intuition, I won't go in here, but it's connected to D-separation. All you're trying to do is that Z should D-separate T from Y in a world where T did not have any effect on Y. Right? But I think more commonly, you can understand it as just reducing the common confounders or reducing the common causes between your treatment and outcome. Voila! So now we have our second reduction. So now we are ready. Right? So our second reduction is effect inference or do operator has now been reduced to a conditional expectation. If you know how to estimate conditional expectations, you can also solve this problem. So what I mean by that is we had this weird do operator in our expression. Now it's just reduced to a conditional expectation. The only problem is it's not just y given t. It's also y given w, where w could be high dimensional. Right? And so binary treatment, it could just be simply the expected value of y given t equal to 1 minus the expected value of t equal to 0 when w is kept constant. And so what has happened in the recent past, I would say the recent decade, is that people have gotten hold of this problem and they've said, hey, we really have good estimators for this expression from statistics. Why not use them in this task? And also, since it's high dimensional, why not use some of the latest machine learning methods to solve this problem? So let me talk about two methods here. So the first one, for want of a better name, you can think of it like a synthetic control. Some people call it the T-learner, which is also a bad name. So let's just keep with synthetic control. So let's say you have some outcome and some confounder. Let's just assume one confounder. Right? Make life simple. And t equal to 1 would be orange, t equal to 0 would be blue. You see this data, and just by looking at it, you might feel, oh, wow, treatment seems to affect the outcome. Right? But what we really want to ask is, I want to match this orange guy to this blue guy, and similarly this orange guy to this blue guy. But of course, my problem is, what do I do with this orange guy? It's no one. Right? That's the matching problem that we discussed earlier. So synthetic control idea says that we'll do estimation. Right? So we'll first just look at the data only with t equal to 0 and fit a line, or fit a regression, fit a deep learning model, whatever you like. And so you'll fit the orange line for the treated people. You'll similarly fit a blue line for the untreated people. And so remember, one distinction is we are not fitting a model combining the treated and untreated. Right? That would be the naive way or the normal way of doing it. Here, we are building two separate models, one for t equal to 1 and one for t equal to 0, with all the confounders. Right? And then you can approximate the causal effect as simply, if you knew y equal to 1, then you take the predicted value of y when t is 0, and vice versa. Right? So essentially what you're doing is that you're creating a synthetic pair for each input based on some machine learning model. Right? And just to make one thing clear, right? So now you might be wondering, hey, what is this? Right? So first this guy told me don't fit a direct model. That's not a good idea. Now you're fitting two different models. What difference does it make? Right? So I think it does make a ton of difference if you look at this example here, this graph. Oops. So look at this graph, right? So age is one of our confounders. So age is W. If you just fitted a model for Y using both T and age, you don't have any statistical control on whether T will be highly weighted or age will be highly weighted, or what might be the relationship between two. It might just depend on your random seed. Like sometimes you might get different answers, right? But what we are now doing is slightly different. So we are saying like, keep T fixed. I want to estimate how age affects Y. Similarly, keep T fixed for the second value. I again want to estimate how age affects Y. And the actual effect of T, I'll calculate on my own. Right? So I think that's the difference. So it just gives you more control in the exact quantity that you want to measure. And then, in some sense, you can think of even advanced methods to do this. And I think today, one of the most common methods and the most recommended one, if you want to solve this problem in high dimensions, is this debiased ML estimator. And it takes this approach to the extreme, in a way, right? So the standard predictor was just Y equal to FTW plus epsilon. I already just described to you why that might not be a good idea. So the debiased ML approach by Chernozyakov et al. Says, let's break down the conditional expectation into two prediction subtasks, right? So again, what you might say is, I know both T and Y are affected by these Ws, right? Here's what I see. Like this is a confounder in both. So why not just, in the earlier method, we just had the outcome modeled as a function of W. Hey, I can also model the treatment as a function of W, right? So the way to think of it is that these Ws are commonly causing both these variables, and that's why you can't directly compare them, right? What if you fit a model that just removed the influence of W from these variables, right? So you get these so-called residuals of Y and T. That's the intuition, right? So I first fit a model from Y to G of W, and I get this Y tilde. Think of it Y tilde as the part of Y, the part of the outcome that is independent of the confounders, right? Similarly, I can fit another model T tilde, which is H of W, sorry, T, which is H of W plus T tilde, and think of T tilde as the residual, the part of T that is not affected by W. And so now you have this nice part where you have Y tilde and T tilde, which are almost as if they are unaffected by the confounders, right? Assuming your G and H are expressive enough, and they have really removed the value effect of W. Once you have that, you do this sort of residual regression, where you have the residual treatment on the x-axis, residual outcome on the y-axis, and now you can fit a standard, even a linear regression model, and that beta that you get would be the causal effect, right? So just to differentiate it again from the standard predictor, you're actually predicting the part of Y that could not have been affected by W from the part of T as well, which was not affected by W, right? And so when you do that, you essentially get just the effect of T on W. Does this make sense? Any questions on these kinds of methods? Yeah.
Hi. I noticed during the synthetic control method you were mentioning, you mentioned that if there's no good match, we create it ourselves so that there's a pair. I wanted to ask if there's any like statistical impact to creating set synthetic pair within the data set. Would it affect our distribution of the data set?
Oh, that's a good point. So we don't actually add that data. It's just a computation that we are doing. So obviously, it is kind of trying to estimate the distribution of Y when T and W both are fixed, right? So that's what it's doing. It will not change the distribution of your data if you have a very good estimator of this conditional distribution. So I think that's the assumption this method makes, that when I fill something here, it actually is following the true distribution.
So basically, the computation of the estimator is based on the current existing distribution, and that yes. The computed synthetic pair would fit the existing distribution, yes. Not altering any of the data.
Right, yeah. So I think the difference just is it's the conditional distribution on both T and Y, yeah.
Hello? Okay.
Yeah.
Does this require, like on the bias ML, does it require that W be observed?
Which one? This method or which?
Oh, the next one. Yeah, so does this require W, the confounder, to be observed?
The W, you mean?
Yes.
Yes, yes. You need all, it assumes that all of the confounders are observed. Yes, that's true. And I think in practice, the answer is like, just try to include as many as you can, and that sort of tends to diminishing returns once you have enough confounders. Yeah.
Yes.
May I ask a follow-up questions on the synthetic control?
Sure. Yeah.
So if you are considering this toy example, what would be a justification to use extrapolation? Like if you see the plot in for the orange dot, now you're trying to use extrapolation on the left side, and let's say that you're fitting this with a quadratic or a third degree order, you might have a very bad prediction outside.
True.
So what would be the justification for that?
So here I think the assumption is that we are already good at cross-validation and predicting data. So this method is assuming that you're following the best practices of machine learning, where you would perhaps not fit an over-parameterized model. You would, okay, this is a bad example because the data is too few, but you have a large enough data where you can do cross-validation and make sure that the method that you picked is a good one. So all of that still needs to be done. Think of these methods as reductions, right? So what they're saying is, if you want to do causal inference, that is hard, right? But we know how to do prediction well. So if we use all the best practices of building predictive models that we know, we can reduce the causal inference problem to this prediction problem. I think that's all we are saying. But the challenges of building a good predictive model, if you have data like this, still exist. Yeah.
Yes. Questions on the use of the synthetic pair. Do we need to ensure that the pair that we generated somehow to have a match with the observations are valid, such that it exists in the, or can exist in the real world and stuff like that? Yeah.
Yeah, so yes, I think you need to do that. And there are multiple ways in which you can do that, which are already established in, let's say, machine learning, right? So one example could be you take off some holdout data and measure whether the distribution of your predictions are also matching that holdout data. But you only do it one by one, right? So you only do it either for blue at once or separately you do it for orange. Yes. But within those, you have to check. You have to check the predictive distribution, does it match or not? You can check the error. You can check average error on the predictions versus what your model is saying.
Got it. Yes, another question would be that do the match have to be stable in the sense that one instance have to match with another instance, but not the third instance?
Not really.
Okay.
It's just, I think the match was more like an intuition to provide the concept. I think in this case what's happening is you are comparing the observed value to a model estimated value of that outcome, right, under a different treatment. So it need not follow sort of any kind of nice properties, as well as in expectation, it's a good approximation. Some people also, in fact, I mean, it doesn't need to be one quantity. You can train 5 models and take the average of that. That's also valid, right? So you could do ensemble models as well. You could also do k nearest neighbors. So I think all of those options are open. But the nice part is that those are options where you can evaluate the performance, right? So you can do cross-validation and find which one fits my data better. Yeah.
Hi. I presume for DML, both W, the confounders, are the same in both equations, right?
Correct, yes.
And I'm just wondering, suppose if W is high dimensional, and it's, say, there are 100 features in W, 99 of them predicts the outcome really well, and only one predicts the treatment. For example, let's just take the very extreme case. Would including 99 other variables in the prediction for the treatment affect our estimate for beta?
So you might think theoretically that, yes, that should be a problem. But what people have found in practice is that as long as you have enough data, including even unrelated confounders, only just helps in reducing variance, nothing else, right? So I think it's one of the puzzles. I think theoretically, you can always say like, hey, this is increasing the amount of data I need to estimate this simple thing, right? That is true. But I think in practice, what the kinds of problems that people see more and more have a lot of data. Like the problem is not only you have 100 samples, you have thousands of samples. So what ends up happening is with over-parameterized models, those variables just help you reduce variance. So in practice, it does not matter. In fact, the recommended thing is not to think so much about which should I include in T, which should I include in the model for Y. Just include everything, but use good non-parametric estimators with good cross-validation. I think that's important. Okay, so just keeping up with time, I think I'll do root cause attribution as the next application, and then we'll break off for 10 minutes, and we'll continue with this presentation after the break. So now we talked about decision making, right? So now you are good at predicting the effect of any decision, but in many cases, you are called in when a decision has already been made, right? And you want to learn for the future. So let's say I wanted to find the effect of A on B, easy. I figured out how to reduce it to a ranking problem, then I figured out how to reduce it to a conditional estimation problem. But if you want to do attribution, it's a very different kind of question, right? Why is it different? So the question might look like this. So given that B is equal to B, I've already seen it, and C equals small c, how would B change if C was changed, right? Now let's come back to our favorite expression, this long expression that you want to estimate. And I don't think there's any ready available answer in statistics, right? That if this kind of expression exists, how do you model it, right? So let's just unpack this, right? Why is it so hard? So why is it so hard to look back in time and imagine an intervention? So it's so hard because intuitively think what will happen, right? So one way you could think of it is, hey, what is this? I'll just ignore the observed effect, right? I'll just build a model for predicting what will happen if C is changed to C dash. I'll propagate the effect and find the value of B, right? Sure, you can do that. So you take C, you sort of propagate through A, you propagate through C to B, and then you can say, it's very simple. If you want to change B and you've already changed C to C dash, the value will simply be probability of B given C. This is from the backdoor criterion we just saw. What's wrong in this? Well, the wrong thing is that this is not well specified, right? We already knew that B is B in the real world, and C is small c in the real world, but this has no information about it, right? For all you know, this might just be estimating some value of B, which if you put just C equal to C here, it would not follow the real value, right? So that's a problem. So the real way this is hard is because you don't just want to estimate the value of like C equal to C dash, what happens to B. You also want to make sure that whatever model you have, if you just put in C equal to C, it should give you the real answer, like the real observed data that you have seen, right? And so this constraint means that we somehow need to model the functional relationships as well. Just the graph won't do it. You need to make sure that you also match the real values. And so here's what is the proposed algorithm, again from UDA-Pearl. I think a lot of the fundamental advances in this field have been made by him and his collaborators. And that's why I'm not even including sites. But I think that the basic algorithm for counterfactual generation goes like this. You have some SCM, which is a structural causal model. So now we are moving one step ahead in terms of assumptions, right? So we are not just need to know what the graph structure is. We also need to have reasonable approximations of the true functions that modulate these relationships, right? So here I might say A is some G of C plus epsilon, B is some F of A and C, and again some epsilon 2. Right? So how do you find out now the changed value of B? You first do abduction, right? Given that you know that A is small a, B is small b, let's first try to find out the errors in this term, right? And the errors are essentially saying what's the state of the world when I was computing the real observed variables, right? So you can do epsilon star is A minus G of C, and epsilon 2 star is B minus F of those variables, right? Then you do the action. So this is the common part. You just set C equal to C dash. And then the prediction part now rolls over this graph. It goes downstream from C. It will go to A. It will go to B. And interestingly, what you're doing is you're using this error that you calculated in the first step. Right? So the difference here really is in the third step, where B dash just does not depend on the new value of A dash and C dash. It also depends on how the world was at the time you were measuring B. Right? A good way to understand this is that the answer will change depending on whether I'm asking, let's say, I observed the value of B, let's say it's air pollution, right, today. What would have happened if I had introduced the policy, government regulation, last month, right? So then you have to model epsilon star as the variables of this month. Right? What kinds of other variables existed this month? Maybe the weather, right? But if I ask you a very different question, if I ask you, hey, I know the observed air pollution also 2 months back. What would have happened if I implemented the government policy 1 month before, meaning 3 months back, right? So now you can't just apply your same model, because now you have to change this epsilon star. This epsilon star has to be whatever it was 2 months earlier. That's the intuition. And of course, I mean, this epsilon star is unobserved, and that's why you need to model it using some known functions in your graph. If some of you are scared, that's good. I think it's a correct reaction. I mean, because earlier I was saying you need to know the graph. Now I'm telling you that you also need to know this G of C, F of C, F, and all of them need to be correct, right? But that's the reality. I mean, it's kind of a proven result. So again, Udapol and his collaborators have proved that if you want to estimate this quantity correctly, the counterfactual, you need to know the SCM functions as well, meaning without them, it is not possible to estimate it. But again, we'll try. I mean, we are hopeful. We are hopeful of better solutions in the future as well, but we'll try, right? We'll try to understand how to do this efficiently. So you can now reduce this root cause attribution problem with using a similar trick. You'll just make it ranking over counterfactuals. So if I have multiple possible actions I could have taken in the past, so it could be x1, it could be x2, it could be x3, I'll compute them separately. So I'll compute the counterfactual value of y if x had been x1 instead of some other value. And then finally, I'll just rank the counterfactual effect of these different variables. So if you had to find out what was the reason that y suddenly increased, or what was the reason that y is so low, you will try all of these possible causes one by one, and then whichever gives you the highest effect, you can answer that, or you can also give a ranking of the different root causes. In practice, some people, especially when you have many of these x's, you can also average over all possible configurations. If you're familiar, it's called the Shapley value. I won't go into it, but that's another reduction you can do. Right? Rather than just computing them separately, you can do it over all possible configurations and compute the Shapley value. But the challenge remains the same, right? So we first got a hard problem using the do calculus. We reduced it to a ranking problem. And now the only thing left is we have to reduce it to an estimation problem. And here I'll give you one example where it seems reasonable, right? So I won't try to explain the real world. I won't give you an example of air pollution or cycling, etc. I'll give you an example of machine learning. Machine learning models also need to be attributed. You also need to understand why they're doing what they're doing. And the best part is, because you build the model yourself, you have that F, right? So counterfactual analysis, what I found, is much more practical when you're dealing with systems you built. It could be a machine learning model. It could also be a large simulator, and so on. But if you want to understand how they work, you want to do root cause analysis, this is very useful. So what I'll do is I'll talk about explaining machine learning models using counterfactuals. And then the next part, I'll also give you an example of explaining a website you built, like a microservice architecture, and you just want to understand why is it getting slow today? Why are users complaining? That kind of thing you can do using counterfactuals. So let's take another motivating example here, just for a second. because counterfactuals only make sense if you have something complicated. I think if you take a very toy example, you won't really appreciate the power of counterfactuals versus just doing logic or common sense reasoning. So let's take this face classification task. So consider someone has built an image classification model where a face is the input, and then it produces some classification. Maybe it's a job application, right? I don't know. But it definitely seems a bad idea to use the face. But let's assume that that's what you're trying to investigate, right? You're a regulator. You have seen this model from a company that's using the face and predicting the job. And you want to check whether it's biased or not, or what exactly is the features that are being used. More realistically, think of it like a resume. So a resume has many things, but it also has the face. And you want to find out if the face is really capturing the causal, is contributing to the prediction or not. So in practice, someone may also ask about explainability, right? The way you might do this is you might look at important features through explainability methods. There are lots of them, right? SHAP and LIME are two common methods that people use. But the problem is they will just tell you, hey, here are the important features, right? Maybe they'll say the name is very important, right? Maybe they'll say their resume title is very important, blah, blah, right? But they don't really tell you how the model will behave if I change this person's face. Right? As humans, this is how we reason, right? If I say this is the root cause, what it means is that if it wasn't there, the outcome would be different. But current explanation methods don't really give you any such information. They would just tell you the ranking of features by their importance. Right? What you would want is something like this. So you would want to say, I changed the image somehow, and actually this is a real experiment. I'll tell you the details later, but this is the same woman who now is wearing a hijab. And so now you want to just put this picture also in the machine learning model and ask how much does the machine learning model predict now, right? And obviously, if it sort of predicts 0, then there is a bias, right? So the background is that this is actually a real study done in Germany where people were trying to find out the effect of sort of facial markers like a hijab on how likely is it that employers will return back for a call for an interview, right? And this is exactly what that social science researcher did. I think her name is Doris. Where they looked at whether sending the exact same resume with this picture or the other picture would lead to a different response rate from employers. Right? So in this case, they were looking at the real bias in people. What we'll try to look at is, can we do the same for machine learning models as well? So the whole trick here is how do we generate the counterfactual? And now we'll have to go back to Perl and look at this algorithm again. Some parts are simplified. Some parts are like G of, there's no G and F. There are not two things, there's only one thing. There's a one machine learning model. There's only one F. But now let's just try to go through the steps of these three things. So basically, the reason we are generating counterfactuals is because if we can generate counterfactuals, we can also explain models in a much more direct way. We can literally make claims of the kind that this image or this part of the image is causing the model to change its prediction from blah to blah. And if this was not there, that's the counterfactual. If this was not there, the prediction of the model will change. So let's assume, for simplicity, it was just tabular data. It was just names you wanted to understand. Like, does the name of this person matter? Sandra Bauer. Very easy. Just change the name. No need for anything complicated. Just change the name, right? But for images, it becomes hard. Suppose I want to change this person to this person. The only thing that should change is the hijab. Nothing else should change. Same person, different outfit. How do you do it? So I think in our case, we use something very simple. There are diffusion-based models available now. They were not available when we tried it. And so we just used an adversary-learned inference model where there is an encoder which takes in X and attributes. X is your image. Attributes are things like headgear, eyes, smiling or not, and so on. So you take this to an encoder, and you get Z. So in a sense, Z is your internal representation of what this image looks like. And then you have a generator which generates another image, X hat. Right? The generator, interestingly, also gets
some noise, which is what we are modeling as the Z, right? So if you follow the Pearl's algorithm, what we would want to do is, given any new image like this, we first put it through the encoder to get our Z. So this is like our error, epsilon, right? So this tells us the true images, the true attributes of this person, which are encoded. Then we also have a counterfactual, so now we change the attribute A. And so now instead of just going directly from A to encoder, you're also going to the generator, right? So now that's our action, which is A to A dash. And then finally, the prediction is done by the generator. So given the same person, all the encoded attributes are the same, just one of the attributes change, the generator can now give you a new X dash, which hopefully only changes that part. The math, I think you don't need to go into, but if you know the generator GAN architecture, I think it's essentially that's what we are doing. The generator is being trained adversarially such that it's able to generate more and more images of different attributes, only changing those. So let's see how it does, right? So we took our counterfactual algorithm and applied it to celeb A dataset. We did not have the German dataset, but this is a very common dataset available on the internet. It has photos of people, and it also has 40 attributes like hair color, skin color, and so on. So we generated counterfactuals for each image. Here's how they look like. So this first image is the original image. And then we can increasingly change the attributes, like we can make the hair black. We could also do black hair and pale skin. We could do blonde hair, and so on. So 2 comments. 1, the system seems to kind of work. You would see the changes in those images that we wanted. But 2, it also looks very blurry, right? And I think that's just a matter of us not being great at image algorithms. I'm sure if someone else tries a better model for generation, they can get much more nicer images as well. But the concept remains the same. And so now we can do some interesting things, right? Suppose someone gave you a classifier and said that, oh, this is my classifier. It looks at faces and recommends some class or predicts some class. Can you explain it? Can you tell me which attributes are considered the most important? And if you're a regulator, you can also ask, is it fair? Like, for example, if I change someone from original to pale skin, does it change the outcome? Right? Usually, if that happens, that's a bad thing. And so here's how counterfactuals can help, right? If you only had an explainability method which did not include counterfactuals, you would also get some bar plot like this, right? So you would get like, oh, pale skin seems to be the most important feature. Chubby seems to be less important, and so on. But I think what's different here is that we are also giving you the guarantee that this is the expected difference for the same person if or not they had pale skin, right? So in this particular model that we studied, it turned out that pale skin was the highest causal, was the highest root cause, in the sense that including it or not including it in the same person would change the model's prediction by the highest amount. There are others as well, and so looking at that, you can look at what your model is learning, you can improve it, you can debug it, and so on. In fact, one of the powers of counterfactuals is that the debugging is also obvious. So if you find that this is the problem, like pale skin is having a really high effect, you simply add a regularizer. You say that for these 2 images, which are exactly the same except that one of them has pale skin, the representation of these 2 images should be the same. It's a very easy trick. A lot of people use it. But it works here because you know that nothing else is different, only the pale scale is different. So you can just regularize and remove the effect. You can also look at fairness. So you can use the same metric and compute standard fairness notions. And so here you might find, for example, pale again comes up as a big important feature. And that's a bias that you can calculate and improve that as well. And so this example was just to show that counterfactuals can be used in cases where you know the functions. Especially so in machine learning, I think they have a very good role to play in explaining the models that we have. So with that, maybe I think we can take a break. And I'm here, so if I think more questions, you can just come up to me and ask.